Yan. I think it's recording now. No? Okay. Okay. So good afternoon, everyone. Welcome to the first walkthrough sessions. No? So the way we conduct the walkthrough sessions, and let me change my screen. Di pa tayo dito. Okay. So the way I usually conduct these walkthrough sessions is papakita ko yung worksheet natin or kung merong practice problems yung gagawin natin. Pero basically what I'll be showing is the worksheet. Tapos kumbaga bibigyan ko lang kayo ng idea on how to solve them, no? So hindi ko papakita yung actual answers, pero if it's a practice problem then I can show you the answers, no? Pero pwedeng hindi complete yung answers. Okay? So para lang mag-guide kayo kung if you ever nagawa nyo na yung worksheet, ma-confirm nyo kung tama yung ginawa nyo, or kung gagawin nyo pa lang, alam nyo kung saan kayo magsisimula, no? So ganun yung magiging workflow natin when we do this worksheet sessions, no? Okay? And of course, if you have any questions na kunwari you've done the worksheets already, tapos meron kayong medyo nahirapan na part, pwede nyo itanong din dito sa natin, worksheet session or synchronous session. Okay? So let's begin. We begin with worksheet number 1 for module 1, which is just a review of the basic concepts. No? So let's start with this first one. Uh, merong binigay na stress strain diagrams, no? So there are 3 stress strain diagrams, and these are engineering stress strain diagrams, no? And these are compressive compressive tests, and this is taken from Little in 2008. No? Okay, so we are to consider the cold rolling of a slab of metal that has an initial thickness of 20 centimeters, and we need to consider the effect of elastic strain recovery, sometimes known as elastic rebound, no? And we are doing all of this at room temperature. Okay, so obviously if we're doing it at room temperature, then the first thing that comes to our head is dapat yung etong graph na to, etong top graph yung gagamitin natin, no? Because it's the graph that is uh, related to room temperature. And before I continue, may tanong ata si Oyi.
Sir?
Yes, go ahead.
Module 3 po ata yun naka-share po sa screen po.
Module 3, I'm so sorry.
Okay lang po.
Wait lang. Bakit module 3? Let me... bakit module 3? Let me, i-shift ko lang. Thank you, Oyi, no? Shift natin sa... okay. Ito na pala. Okay. So ito yung module 1. So ulitin ko lang, no. So ito yung problem natin. Meron daw tayong slab of metal that has an initial thickness of 20 centimeter. Tapos gusto natin sagutin tong questions na to knowing that we are doing it at room temperature, and kailangan natin i-consider yung elastic strain recovery, no. Okay? So meron tayong graph na binigay dito, and there are 3 graphs, no. Merong one that is done at pwede natin tawagin to as as ano bang term dito, warm working. Tapos itong isa is hot working, no. And this is yung cold working. Cold working usually pertains to when you're doing it at room temperature. Okay. Okay, and just to recap, no, ang difference between warm working and cold working, warm working and hot working is kasi essentially meron lang talagang dalawang types, no. We have the cold working and we have the hot working. So if you're doing your parang process at conditions wherein it is above recrystallization temperature, then we consider that as your hot working condition, no? Tas anything below is cold working. Pero right now merong parang bagong term na ini-introduce, yung warm working. So warm working is just any temperature that is above the room temperature pero hindi siya high enough to reach the recrystallization temperature. Pero essentially warm working is the same, halos same lang yung mechanisms involved with room temperature, no. Although because of the higher temperature, may chance na mas meron siyang konting annealing effects or softening effects, no. Okay? Pero that's for another lesson, I guess. And I guess na mas na-explain to sa MetE176 nyo, no. Okay? So, start tayo dito. before we can begin to answer this question, siguro i-imagine muna natin kung ano nangyayari dito sa metal natin. So if we tako dito sa Photoshop ko na. Okay. So siguro with your survey of yung kasi module 1, tama ba? This is module 2 na dapat to, no? I know that tama, module 2 na pala itong worksheet 1. So module 1 was the survey of adaptive metallurgy techniques. Tapos si module 2 is parang review of basic concepts. Okay? So from your survey, di ba pag meron tayong kunwari meron tayong 2 rolls. So this is a rolling operation, no? Tapos meron tayong slab of metal. Tapos yung slab of metal papasok dito sa rolls. Then it reduces in thickness, no? Tama? So there is a reduction of thickness. Tapos the amount of reduction will depend on how large this gap is, no? So this is the roll gap. And yung amount of strain na na-experience ng material na to will be equal to, and if this is the initial thickness, no? So ang strain equation kasi natin, and for this case we're talking about yung lateral strain, so along the thickness. So our strain here will be equal to yung initial minus final over initial. So that's how we usually express our strains, no? So lalo na pag engineering strain yung pinag-uusapan. Okay? So pag ganyan, if this is the equation, and minsan pwede ring final minus initial, no? Depending kung compressive siya or tensile. Okay? So a more general form is parang naka absolute values. Pero for us, we'll just use this form, no? Kasi mas malaki yung initial natin over as compared to the final na strain. So if this is the case, ang actually hinahanap natin is kasi yung the problem, let me go back to the problem, no? For problem 1 is we need to approximate the final thickness, no? So for us to be able to get the final thickness, kailangan muna natin kunin yung strain. So actually, ito yung hinahanap natin, no? So this is what we're looking for. And if we find this value, then we know the initial and we can determine kung ano tong final. Tama? So by the way, have any of you done this worksheet? Meron na bang nagsimula sa worksheet na to?
Ito namin kagad.
Si Ray, sorry Ray, nagsimula ka na? Or tapos mo na?
Tapos ko na po pero di sure.
Okay. Pero based on what I'm discussing now, ganito ba yung strategy mo? Bakit may nag-thumbs down ka, Lloyd? Grabe itong Lloyd na to.
Di masyado, sir.
Sige. So, try lang natin kung baka iba yung approach mo, pero basically we did the same thing, no? Okay? So, we need to find the final na so again, hinahanap natin itong final. This is what we're looking for, no? Ito siya. And to do that, kailangan kasi natin i-take into consideration yung elastic rebound, no? So, let me try to explain what elastic rebound is, no? And hopefully this is already covered sa either 176 or sana na-cover to sa 176, no? So for example, if you have something that looks like this is a stress strain diagram kunwari of a hypothetical metal lang kunwari, no? So if we do a tensile experiment or compressive experiment, depending on what you are doing, no? You will find out that if you put a stress, kung nag-stress tayo, tapos kung tumigil tayo dito, tapos in-unload natin yung stress natin, tapos ni-release natin, you will notice na yung metal natin will actually have zero strain, no? Parang zero strain siya kasi nandito pa tayo sa elastic region. So lahat ng strain na nangyari sa kanya is mababawi lang. Tama? Now what happens if, for example, ang ginawa natin is we do the straining, tapos umabot tayo sa point na yield na siya. So we are in the plastic region, ano. So lumagpas na siya. So meron na tayong plastic strain, no. And lumabot na tayo dito. Tapos ginawa natin is in-unload natin yung load cell natin, no. So unloading meaning parang tinigil natin yung test tapos inallow natin na bumalik yung metal natin sa original size niya. Okay? So what actually occurs is if I draw a line parallel to this this linear portion, I can actually determine kung alin yung part na ma-recover niya. So if and let me just move this around now. So para mag-start siya at 0. So ito actually, if I measure this strain right here versus yung strain right here, bring this down. Meron tayong 2 strains na involved, no? Okay? So ito, this is actually is this elastic or plastic? Tingin nyo. So we have elastic and plastic strains. So just a review, no? Pag plastic, sinabing plastic, this is permanent type of strain. Pag elastic, this is temporary, yung nababawi siya, no? Tama? Naalala niyo pa yung 2 types of behavior, elastic and plastic behaviors?
Yes, sir.
Okay, that's good, Eddie. So ito, tingin nyo, ano tong part na to? This one. Is this elastic or is this plastic? Eddie? Tingin mo.
Nag-raise po ng hand si Owen. Pero tingin ko po, plastic.
Tingin mo plastic. Okay. Bakit plastic siya, Zeddy? Dahil nasa right side?
Kasi yung point niya po ay nasa plastic. Sa plastic region.
Okay. So yun yung some of the misconceptions, no. And in fact ako din, kahit ako nalilito din ako dito, no. Pero actually tama si Lloyd, no. This is actually elastic, no. So this is the elastic and this is actually the plastic. So elastic siya kasi siya yung na-recover mo. So if you notice, etong lahat ng strain na to, na-recover natin. Tama? Kasi if you notice, yung metal natin bumalik siya up to this point. So if we try to measure this, kasi strain diagram, actually yung mini-measure nyo lang talaga dito is amount of force versus delta L. Tama? Ganun lang nag-measure ang ano eh. Tapos kaya lang nagpo-produce ng curve na to, ginawa nila is dinivide nila by the constant area, which is area naught, tapos dinivide nila by the initial length. Okay, so technically, ang binemeasure lang talaga ng equipment natin for the UTM is actually the force and the L naught. So that's why yung engineering stress, hindi niya na-take into account yung necking, hindi niya na-take into account yung yung instantaneous na stresses involved, tsaka hindi niya na-take into account yung infinitesimal na strains involved. Okay, kasi ito lang talaga min-measure na F and delta L. Okay? So if you notice, so if you look at it in terms of delta L lang, so parang sinasabi natin dito, yung lahat ng delta L na to, dito sa portion na to, binawi na lang lahat, parang na-cancel out. Tapos ang na-retain lang talaga is this delta L right here, or kung i-divide natin by L naught is the strain, the plastic strain. Okay? So medyo nag-mix, we did the experiment again. Tapos this time, ginawa natin is, nag-extend tayo hanggang dito naman. So dito na lang. Kasi beyond UTS, medyo hindi na natin ma-expect yung same behavior, no? Because if you remember si UTS, so naalala pa si UTS is ultimate tensile strength, siya yung parang highest peak or point dun sa stress strain curve natin, no? And what happens here is nagkakaroon ka na ng tinatawag na necking, and necking usually involves microvoids, no? Wherein nagkaroon na ng parang internal cracking yung ano natin. And kumbaga, meron na dahil may microvoids, may stress concentrators ka na, so iba na yung expected behavior na supposed to yung bulk material natin na wala pang defects. Okay, so kaya in most na stress strain diagram, usually beyond UTS, medyo iba na yung behavior na, lalo na kunwari ipag-convert natin to into in fact, if you convert this into true stress and strains, diba, pag true stress, true strain, always increasing siya up until UTS lang actually. So beyond UTS, behavior na lang siya. So parang kinukuha yung I believe last slope, or depende sa sa type of modeling na ginawa. Pero ang pinaka-common na is kukunin lang yung slope tapos i-extend lang siya pag ganyan hanggang fracture. Ganyan. So ganun ginagawa yung So UTS just signifies na yung nag-breakdown na yung behavior ng metal natin, or hindi na siya yung bulk na behavior talaga without defects. Okay? So, siguro narinig nyo na rin to, no? So, while we're on the topic of UTS, narinig nyo na rin na si metal natin, hindi siya, how should I put it? Pagka nagko-compute tayo ng true stress, so naalala nyo pa yung true stress to So if this is sigma, let's call the true stress as sigma, no, and the engineering stress as S, tapos epsilon ang true strain, while E ang ano, dapat pala E yung ginamit ko dito. Sige, para mas consistent tayo. Sigma T na lang ang true stress, sigma E ang engineering, tapos epsilon T ang true strain, tapos sigma E ang engineering. So naalala niyo yung relationship between the two? Sinong nakakaalala? Sigma T is equal to, tama ba? ln1 plus epsilon E. Tama, no? Tapos, and ginawa natin to sa 176 ata. Parang nag-derivation tayo. Kasi ito, 1 plus epsilon. Tama, no? Correct nyo ka. Pero I think that's correct. No? Nag-agree ba kayo? Meron naman nag-confirm. Okay? So, later ano natin kung paano yung equations na yan. Pero for this, hindi muna natin siya yan. Napadalawang isip tuloy ako. Tama po tayo. Sige, i-double check natin. Pero I think that's the correct equations. Anyway, ano ba yung ano ko? So ito, nag-work lang tong equations na to, itong relationship actually before UTS. No? After UTS, hindi na applicable or valid. Okay, so balik tayo sa experiment natin. No? Ang ginawa natin is we loaded our sample. Umabot tayo sa point na to before UTS. Tapos ang ginawa natin is, so malaki na yung plastic strain natin. Ito is unrecoverable, no? So permanent na to na strain. Pero may certain portion pa rin na recoverable, which is this one. No? We bring it down. This is still elastic strain. Tama? Tapos itong malaking part na to, ito na yung plastic strain natin. Okay? So, with that, dito sa problem na to, kaya na natin ma-determine, no? Tama? So, if we know, if alam natin itong roll gap natin, so we know yung maximum strain na dapat ma-experience na once it enters the roll gaps. If we look at the, ito. So, pumasok siya dito. So, parang ang nangyari dito is, pumasok siya once it enters. So, nandito siya. So, pumasok siya na ganyan. Then, it becomes deformed. Umabot siya dito. Then, after that, nagkaroon siya ng rebound, which is akin to saying na nirelease na natin yung load natin. Paglabas niya dito. So, yun. So, based on this information, tingin nyo kaya na siyang isolve? Nag-make sense na ba?
Parang nawala ako dun sa may rebound part, sir.
sa rebound part. So, ulitin natin. No? So, para ang nangyari is, sige, ipapasok natin yung metal natin. No? So, pasok natin yung metal natin. So, yung metal natin, unstrained pa dito. No? Tama? Unstrained siya. Kasi wala pa namang forces na involved. Tama? So, pagpasok mo dito sa portion na to, ito may mga compressive loading ka na. No? So, itong compressive loading, nag-apply ka ng stresses. So, tumataas yung value mo. Tama? Tumataas. Tapos up to a point na, i-deform niya kasi made-deform siya dito eh. So, made-deform siya, papunta dyan. Tapos, up to a certain point, kasi paglabas niya dito, na-deform na siya, paglabas ng compressive load dito eh. Tama? So, kumbaga free na yung material natin. So, unconstrained na siya. So, parang it's akin to saying na kung i-ano natin dito sa natin, graph, para siyang in-unload natin. So, gagano na siya. So, with that, dapat kaya nyo nang i-solve tong first problem. Tama? So, hindi ko papakita yung exact solution. So, I'll leave it to you guys para i-figure out kung paano siya masasolve. Pero parang ganun yung ano niya, yung dapat parang strategy. So, Ray, tingin mo, since ikaw yung nakagawa na, no? Is it similar to the method you employed or medyo iba siya?
Iba po, sir.
Sige. So, try mo na lang kung try mo tong method na to, tapos baka i-compare mo kung similar ba. Pero and I'll ask this for everyone, no? So, do you think the method or itong parang direction na to make sense? Or meron kayong apprehensions? Make sense naman. Oh, thank you, Lloyd, for the feedback. Iba, Oyi. Okay. So, yun. If you have any questions pa, then you can ask me anytime, no? Pero I think okay na tayo sa problem 1. Pwede tayo mag-proceed, no? Okay? So, for those who came in late, so, ganito yung way na pag-conduct ko ng review sessions or worksheet walkthroughs na hindi ko talaga ipapakita yung final answer, ipapakita ko lang yung parang general strategy of solving the problem and a few basic or review concepts, no, para matulungan kayo. Okay? Okay tayo dito. Okay. So next natin is what is the expected yield strength of the rolled metal? Okay? So for this, kailangan ko i-review ulit yung ano, no? Review ulit natin and let me delete my canvas, no? Oh. And para lang alam nyo kung ano yung question. Ito siya. So the question is, what is, itong question number 2 natin, no? What is the expected yield strength of the, ano? Pwede sigurong copyin ko na lang to. Tapos lipat ko sa parang blackboard ko. Kita nyo ba? Bumalik na ako sa ano, no? Sa parang blackboard ko. Tama?
Opo.
Okay, thank you. So, lagay ko lang dito siya. Okay? So, ang question, so okay na tayo sa question number 1. Proceed tayo sa question number 2. Question number 2 is, what is the expected yield strength of the rolled metal in number 1? Okay, so for us to solve this, kailan tayo ng konting review session, no, sa parang behavior ng metal natin when it is exposed to a UTM test, no? So, for example, let's take our metal ulit. Parang ganyan na metal. This is the stress strain diagram of a hypothetical metal ulit. Tapos, when we load our metal, so kanina nag-experiment tayo, no? Sabi natin, what happens if ganito siya, tapos nag-yield yung material natin. So that means lumagpas na siya dito sa point na to. Tapos tinigil natin and in-unload natin. Tama? Yun yung parang sinabi natin. Oop. Tapos ang sabi natin is, ang nangyayari sa metal is, and siguro pwede ko i-drawing na lang dito diretso. Ganyan. In-unload natin siya. Tapos, pag in-unload natin, ang sabi natin, i-release niya yon, tapos magkakaroon tayo ng yung recoverable strain, which is yung elastic rebound natin. This is the elastic strain and sometimes known as recoverable strain. Recoverable strain. Minsan din tinatawag siyang elastic rebound. Okay? So yun yung mga terms na ginagamit natin, no, to describe this temporary strain na to. Okay? So meron to siyang konting plastic strain, no? Tama? So nagkaroon siya ng parang deformation, na. So if we were to load it again, so kunwari ilo-load natin siya ng ganyan. So this is the same material, no? Ilo-load lang natin siya. So tingin nyo ba ifa-follow niya ulit tong plot na to? So this is the same material, in-expose lang natin ulit sa test. So definitely ifa-follow niya tong ano, no, itong Hooke's law kasi same sila ng ano elastic behavior. Tama? Pero would it follow the same path right here? So if we consider natin yung strain hardening effects, naalala niyo pa yung strain hardening? What is strain hardening? Tawag ako Excel. Naalala mo ba what strain hardening means? This is from MetE176, no?
Ano po, ang naalala ko po sa strain hardening is yung mga dislocation po sa microstructure ng materials.
Mm-mm.
Mas napapalakas niya po yung material kasi pag po may nag-move na, parang hindi na po nakaka-move yung mga next po na structure, na something po sa structure.
Nakuha mo naman yung gist niya, no? Para magkakaroon ng dislocation forest, yung term na ginagamit ng iba. So magkakaroon ng dislocation forest kaya nahihirapan mag-move yung crystalline structures natin. So kaya yung ano, no, nagkakaroon tayo ng hardening effect or tumitigas yung metal or yung tumataas yung strength. Tama? So given na tumitigas yung metal natin, kasi dito meron tayong amount of plastic strain na nangyari, di ba? So it would be we would expect na yung yield strength niya, which is a measure of the hardness or the strength of the material, should be higher. Tama, no? Make sense, no? And 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 if it's higher, then how much is it higher? Yun yung question eh. Gaano ba katigas yung bagong material? So if you actually did this experiment, it will still follow the itong Hooke's law or itong path na to, itong linear path na to. Titigil siya actually dito sa last na strain o last na stress na na-experience na. So itong part na to, so itong sigma na to, diyan actually siya titigil tapos magkakaroon tayo ng panibagong curve na ganyan. And probably it will be shorter no kasi dahil sa strain hardening effects, one of the disadvantages of strain hardening is tumitigas siya pero naging brittle. Tama no? Okay? Nico asks, is strain hardening the same as cold working? Yes, same lang siya in ours. Strain hardening just describes the mechanism no na ng parang pagtigas ng metal natin or pag-strengthen ng material natin. Pero it can also be described as yung yung process of deforming metal to increase its strength. So in some cases they can be used interchangeably, pero in some cases din there are certain scenarios or terminologies na strain hardening lang yung term na pwedeng gamitin at hindi cold working. Pero in general, you could say na parang halos interchangeable sila. Okay? So, eto. So, nakita natin no na parang ganito na yung bagong path natin. So, let's just say na tinuloy natin yung experiment no. And gumano ulit tayo. Tapos tinuloy natin siya hanggang dito kunwari. Tapos in-unload natin siya ulit. If we unloaded it again, so mangyayari, ipa-follow ulit niya yung path na to. Tapos meron siyang another set of itong unrecoverable strain no, or permanent strain. So if we were to do the experiment again, ulitin natin siya. Ganyan. Hindi na dito yung yield strength niya ulit. Tataas ulit yung yield strength niya. Nandito na yung yield strength kung saan siya last na tumigil. Okay? Tapos magiging ganito yung itsura ng graph niya. So eventually, parang tumitigas at tumitigas siya tapos nagso-shorten yung niya. Itong parang yung fracture yung sigma F niya no at fracture kasi kumbaga nagiging mas brittle siya eh. So what this essentially means is merong instantaneous stress na kailangan ma-overcome yung material para continuously deform siya. So yung stress na yun, tinatawag natin siyang sigma. Minsan sigma F yung ginagamit, minsan sigma prime. I think these are the two terms na ginagamit. These two means sila yung tinatawag nating flow stress, no? Okay? So maybe you've heard of the term before, flow stress, pero dito sa MetE177 will be using this a lot, no? Si flow stress. Flow stress is again, siya yung instantaneous na stress requirement needed to continuously deform a metal or needed to continue the plastic deformation process. Okay? So if hindi mo ma-overcome si flow stress, hindi ka makakapag-continue deforming the metal. Okay? So nagme-make sense pa tong ginawa kong graphs? So these are experiments that have been done, no? So napakita to na nangyayari talaga siya. Okay? Obviously mayroong mga mga caveats pa dito like kunari yung effect ng kung gaano kabilis yung yung straining kasi pwedeng iba yung rate ng yung pag-akyat ng natin ng yung ba tawag dito? Yung parang head niya. Pwedeng iba yung bilis niya so pwedeng maka-affect yun sa graph pero in general ganito yung magiging behavior niya yung shape niya. So it starts off as meron kang established yield point pero once na nalagpasan mo na yon, you actually have a new yield point. And we call that new yield point as the flow stress. So basically what I'm trying to say here is if we know for a certain unstrained metal, kunwari hindi pa nasa-strain yung metal at ito yung itsura ng graph niya, parang ganyan. Then at any point, if we want to strain the metal, we need to exert this amount of stress. Itong sigma F na to. So for example, if we want to strain it by this much, gusto ko instead of dyan hanggang dito yung stress ko, kailangan ko umabot dito sa point na to para siya, ma-continually strain siya. Kung ma-overcome ko to, pwede na akong pumasok dito sa region na to and so on and so forth. Okay? So that is the concept of flow stress, no? Okay? So I hope that makes sense, no? So with that said, tingin nyo kaya na bang ma-solve to what is the expected yield strength of the rolled metal in 1? Kaya, no? Tama? Mukhang feel ko ilan sa inyo may nagkaroon na ng idea kung paano to isa-solve. Okay? I think okay na tayo dito. Okay? So, next naman natin is what is the minimum allowable roll gap for a fresh workpiece? So, minimum allowable roll gap is gaano ka liit yung kaya nating no? So, if you remember, to yung rolls natin. Gaano ka closely natin siya maipapasok. Parang ganyan. Kasi obviously, if you're an engineer, gusto mo i-maximize to, no? For if it's a parang rolling mill, kunwari, na we have stand 1, tapos may continuous process to, no? May continuous rolling mill siya. Stand 2, obviously, stand 2 dapat mas siya, no? Mas closer tong gap na to. Pero, ano yung disadvantage kasi kung engineer ka, isipin mo, bakit ko kailangan ng 2 stands? What if gawin ko na lang na yung stand 2 is smaller or yung stand 1 ko is this amount of roll gap. Tama? Kasi kung ganito kaliit yung gagawin ko, edi parang unnecessary na si stand 2. Tama? O ilalagay ko siya sa stand 1. So what is hindering me from doing this? Tingin nyo. It's related to yung sinabi ni Excel kanina about yung explanation niya about strain hardening. So tingin mo, bakit hindi natin pwedeng i-get rid na lang tong stand 2? Tapos kunwari lang ang delta M, ang delta H nito is, or ang roll gap niya, the gap is around 10 millimeters kunwari. Tama? Tapos dito, ang gap niya is 30 millimeters. So bakit ko kailangan i-roll muna siya to 30 millimeters bago ko i-roll to 10 millimeters? And while you're thinking about it, so mag-isip muna kayo tapos may nagdo-doorbell kasi ko lang. Ipapasukin ko lang. So think about it . Okay, naisip nyo na ba? Meron bang may sagot? Parang walang may sagot . So, i-guide ko na lang kayo. 'Di ba? Sorry, I'm catching my breath, no. 'Di ba ang sabi natin na mag-strain harden siya? So, one of the consequences, 'di ba sinabi natin kanina na one of the consequences of strain hardening is that it becomes extremely brittle, no? Tama? The more strain hardening you do, the more brittle your material becomes. Therefore, you are not able to do extreme amounts of plastic deformation precisely because of that limitation. Kasi mangyayari is, if you overdo, kunwari ang ginawa mo is masyadong mataas yung strain hardening na in a single pass, ang nangyayari is naging brittle yung material mo, and when materials are brittle, they are prone to cracking or defects, no? Tama? So I think that makes sense, no? So that's why in most industries, ginagawa nila in stages yung yung deformation, no? So for example, rolling is usually done in stages, and sometimes intermittent between the stages, naglalagay pa sila ng parang heat treatment para ma-relieve yung stresses, no, para pwede pang larger amount of deformation. And minsan yung iba hot working talaga yung conditions na ginagawa para hindi magiging brittle yung material. Okay? So in drawing, merong term na ginagamit dito, no. It's known as maximum drawability. So parang sinasabi sa maximum drawability is that may limits lang kung ano yung kayang draw in a single pass or in a single die. Okay, so later on, pagka nag-compute na tayo, no, we will able to compute this theoretical maximum drawability of a particular na drawing arrangement, no. Okay? Narinig ba ko? Naka-on na ba yung mic ko? Thumbs up kung ayan. Thank you, Sedi, Oyi, and Lloyd sa pag-ano. Okay? So with that said, so ang limit natin actually is, kasi ayaw natin maging brittle siya. So in the stress strain diagram, meron bang certain value dito that indicates na naging brittle na yung material natin to the point of having defects? Meron ba? Tingin nyo?
Hindi pa ba dun sa may yield point?
Kung
Or-
sa yield point, ang nangyayari lang kasi sa yield point is nagpa-plastically deform siya, which is exactly what we're doing here, no? Kasi pag nag-roll naman tayo, gusto naman natin mag-plastically deform para lumiit yung thickness niya. So pero that's a good starting point, no, Sedi. So okay lang. So I'm basically saying na itong yield point na to, let's say sigma y. Sigma y, okay lang to. So ano pa bang ibang value dito na pwede?
Sa UTS po ba, sir?
UTS
Pwede
po.
ba?
Yon, UTS. Pwede sa UTS, no? Kasi ang sinabi natin, after UTS, nagkakaroon na tayo ng, if it's tensile, nagkakaroon ng necking, or magkakaroon ng micro voids na siya, which is detrimental na. Sometimes, pwede nilang i-argue na pagka nagkakaroon ng micro voids, hindi naman siya ganun ka, no? Lalo na pag compression, kasi pag in most metals are stronger in compression than they are in tension. May iba din na nag-argue na pwede actually dito sa sigma F. So kayo, it's up to you to justify, no, kung ano siya. Pero yun, sige, hindi ko na i-ano kasi baka parang sinasabi ko na yung sagot, no. So try to read more about it. So you can do UTS or sigma F or sigma F. Bakit sigma F? Bakit epsilon F? Dapat sigma F. So yung fracture strength, no. So try to think about it. UTS pass or sigma F. Parang ganun. Okay? So okay tayo dito sa ano, no. Sa third problem, pwede na yan. So what is the final product thickness at the roll gap in number 3? Okay? So, if you think about it, parang kunwari, kung 30 millimeters tong roll gap, so ang metal papasok dito, let's just say 50 millimeters. Ay, meron palang actual lang, ano, no? Sabi, 20. Tama, 20 millimeters ang roll gap. In 3 pala. So, kailangan nyo ma-solve muna to. So, after nyo ma-solve siya, pero sige, sasabihin ko na lang para mas maano nyo. Actually, pwedeng UTS nga yung gamitin natin, no? UTS. So, from UTS, maano natin yung sigma, yung amount of strain na kaya niyang i-experience. And from there, masosolve natin yung roll gap na to. Tama? Kasi basically, parang delta L to eh. Parang ganyan. Or in this particular case, we say delta T kasi thickness to eh. Okay? So, once na na-solve nyo yung delta T, so if 20 to, let's just say ang na-solve nyo and hindi dito yung exact na ano no na actually dito delta t. The delta is actually this one. This is delta t over 2 and this is delta t over 2. Tama? Make sense ba yan? So if we do the kunwari ang equation natin sa epsilon, let's do epsilon engineering is equal to T naught minus T final over T initial. Tama? So this is equal to delta T over T naught. Yung delta T natin dito is not this one, no? Kasi ito roll gap to eh. Ang delta T natin is actually itong part na to. Kasi dito siya na-deform eh. So nag-decrease yung ano niya, nag-decrease yung ang tawag dito, nag-decrease yung slab by this amount. So, and since we assume na symmetrical siya, so parang delta T over 2 sa taas, delta T over 2 sa baba. So, yung final height natin will just be equal to T naught minus delta T. Yun yung T final natin. No? Okay? T final, which is actually siya yung magiging parang gap, no? Tama? Pero this is assuming wala tayong elastic rebound. Tama? Does that make sense? So, kung walang elastic rebound, parang sinasabi mo kung ano yung final niya na ganyan, ito lang siya. Ito yung buong delta T na yon, delta T over T naught. Tama? Ito siya. Kaso, nagkakaroon tayo ng elastic rebound eh. May parts na nare-recover. So, ibig sabihin, parang if we were to draw the metal, para siyang pumasok na ganyan, na-deform siya. Pero after niya ma-deform, so i-drawing ko, parang, so after niya pumasok sa roll gap, marirecover niya yung ilang parts. So, kumbaga, meron siyang, kaya tinatawag siyang elastic rebound kasi parang nagre-rebound siya. Tama? So, ito actually yung T final. So, kailangan natin i-consider yung elastic rebound, no? Okay? So, I think with that said, kaya nang ma-solve to, no? Itong final product. So, if we know yung allowable roll gap dito, kaya na natin i-solve tong final product thickness considering elastic rebound. Okay? So, okay. Okay tayo doon. So, hopefully, nakuha ng lahat. And with the things I said, sana matulungan kayo sa pag-solve nitong worksheet number 1 natin. And actually, problem 1 pa lang pala to. No? So, proceed na tayo sa problem 2 kasi meron pa tayong isa pa. No? Okay, so I'll just remove problem number 1. Proceed tayo sa problem number 2 naman. So let's look at problem number 2. Problem number 2. But na i-close to worksheet. Ay, sorry. Ito siya. This is problem number 2. And see, problem number 2, I think this is relatively easy, no? So for some metal alloy, a plastic true strain of 0.025 is produced when a true stress of 360 megapascals is applied. For the same material with an initial length of 500 millimeters, how much will the elongation be if a true stress of 405 megapascals is applied? And we will assume a strain hardening exponent value of 0.2. And actually, meron ng clue agad, no? Itong last statement. Okay. Tingin nyo, ano yung magiging pinaka-working equation natin dito? Any ideas?
Yung ano sir, Holman equation.
Pwede, no? Yung Holman equation, sometimes known as yung power law natin. So, yung Holman equation, sino yung sumagot doon? Sorry, hindi ko nakita yung pangalan.
Oy po.
Ikaw pala yun, Oy. Oy, pwede mo ba i-explain kung ano yung Holman equation? Ano yung form niya? It's a power law. Ano yung form?
Nare-relate niya po yung true strain and true stress. Tapos may constants po.
Okay, that's correct, no? So, it's equal to, and pwede ko isulat na lang siguro dito, no? Equal siya sa sigma is equal to K epsilon raised to the power of N. So, actually, ito yung nag-govern sa plastic region natin, no? So, if we look at, if we look at, for example, ito, isang stress strain. Kung dito, ang nag-govern is Hooke's law. So, di ba, dito, this is just equal to a linear equation, no? It's equal to sigma is equal to, ano ba yung symbol ng Hooke's law? Wait. Is it E? Capital E ata, no? Tama? Yung elastic modulus natin. So dito, it's equal to sigma. If you are in the linear region, it's equal to sigma is equal to capital E times E, where E is the elastic, capital E is the elastic modulus. No? Pero once you go past the elastic region, so pagka lumagpas ka na dyan, nandito ka na, ang nag-govern na dito is actually the power law. No? And obviously, hanggang UTS lang. Hanggang UTS lang din siya because beyond the UTS, hindi na nag-work din ang power law natin. Okay? So, tingin nyo, can we solve this? Parang direct lang siya, no? Tama? Direct substitution lang. Kasi you're given N. Tapos may initial conditions ka na true stress and true strain. Therefore, masasolve mo na tong K. Tama? And kung masasolve mo na yung K, then therefore, if you are given the same material tapos meron kang different na conditions, kaya mo na siya i-solve. So, one caveat lang dito is that ang given ata is, tama ba? Yung, tama. Kasi true stress and true strain yung magiging values dapat. So, if you want to find out kung ano yung magiging final na elongation, kailangan mo i-convert yun into engineering terms. Tama? So, if you need engineering terms, so kailangan mo i-convert siya. So, meron ka pang parang conversion na mangyayari. No? So, you'll have to use the relationship between true strain and true stress. Tama? So, itong problem to relatively easy, no? Would you agree? Meron bang nakasolve na nito? And sino ba yung nag-solve kanina? Si Ray. Ray, nag-solve ka na rin, no? And si Nico, nag-ano din eh, nag-thumbs up. So, I'm assuming si Nico nag-solve. Si Lloyd, thumbs down ulit si Lloyd. So, Nico, since na-solve mo na to, tama ba yung thumbs
Sir,
up? Sorry.
parang di po ako nag-convert to engineering if I can correctly remember po. Kasi parang as is naman po yung problem, kaya naman po siya i-solve kahit hindi na po mag-convert sa engineering. Kahit yung true stress lang po yung gamit.
Okay lang naman pero kung titingnan mo dito Nico, ang tanong kasi is how much elongation is needed. Yung engineering yung true strain natin, di ba siya? True strain is the instantaneous, it's L instantaneous over Ln pala, tama? The true strain is instantaneous over initial, and this is in Ln, no? Parang ganyan. Actually, pwede pala kasi yung instantaneous, magiging siya lang yung final. Okay, I agree. Pwede naman hindi na mag-convert, no?
Holman equation lang po ginamit ko.
Kaso, amount of elongation yung hinahanap, ha?
Yes po.
So, delta L, kumbaga, ang hinahanap. So, kailangan mahanap mo na yung final, then i-minus mo. So, I think tama pala si Nico, no? Hindi mo na kailangan i-convert sa engineering. Pero I think you can also use engineering, pero Pero parang additional steps na yata yun. So, I think you can use diretso through strains lang. Okay? So, relatively mas madali itong problem 2 no, kumpara sa problem 1. So, I think okay na tayo dito. We can proceed with stress states na. Okay tayo? Kasi si stress state, medyo mahirap actually si stress state. Okay, so let's proceed. So stress state, ito tayo. So ang gagamitin ko dito, since practice problem naman to, pwede siguro i-solve na natin to, no? So hindi to actually yung worksheet, pero ito yung practice problems na makikita natin sa module 3 mismo. So module 3 is all about stress states, no? Okay, so ito, we are given a element, a stress element. So it's in the XY na ano, no? Work in the XY space. So we can say na ito is isang type of 2D stress state, no? Tama? So this is a 2D stress state. Tapos we are to find the following values, no? So principal stress muna, orientation of the principal stresses. Then we have the maximum shear stress. Then stress state 30 degrees clockwise from the X plane. And we are to plot and label all relevant answers. So ito, kung 2D stress state, ano yung pinaka-easiest way to do this? Tingin nyo. We can use equations, no? Pero Fico, mahirap. Para masyadong mahirap equations. I think we can go with a graphical approach. And the best way, if you do a graphical approach, is more circle, no? So, naalala nyo pa yung more circle? So, more circle is we are graphing our, ano, no? We are converting or we are plotting our stress element in an imaginary tau sigma plane. Tama? So this is a 2D plane. Itong coordinate plane na to, it's tau and sigma. So sigma is positive pagka compressive and negative pagka tensile siya. Tama? So naalala niyo pa yan, yung convention. So that's the convention we'll be using today as well. Tapos, ano yung convention nyo dito? Kasi I think, depending sa teacher nyo sa ES 102, pwedeng magkaiba siya, no? Is it clockwise ang positive? Tapos, counterclockwise ang negative?
Counterclockwise po yung positive. Ngayon pa lang po kami nagtitake niyan, sir.
Ngayon pa lang kayo nagtitake. Okay.
Kasabay po.
Okay, sige. So, medyo, so relatively new sa inyo tong ano, no? Actually, yun din yung convention ko. Kasi naalala ko from last time, parang opposite yung convention ng student sa convention ko. So, counterclockwise is positive. Tapos, clockwise is negative. So, it wouldn't really matter naman dito sa ano, no? Sa more circle as long as consistent kayo. Okay? So, medyo, pero na-discuss na to in some detail kung paano siya nag-work? Or as
Hindi
in,
pa.
hindi pa? Okay.
Ngayong week pa lang po.
Sige. So, i-ano natin kung paano siya nag-work, no? Akala ko magiging review lang to, hindi pala. So, the way it works is, kukunin natin yung, magsaset tayo ng coordinates. Okay? So, the first coordinate na isa-set natin is yung sigma, and this is, we set this as sigma x. Ito yung sigma y. So, ang assumption kasi ng stress state, when we talk about stress states, no, is that everything is in equilibrium. Tama? So, if it's in equilibrium, dapat kung meron kang sigma x na 350 dito, meron actually opposite force na 350 sa kabila din. And these are positive values. Positive siya kasi tensile siya. Ay, sorry. I meant to say pala kanina, no, positive is the tensile, compressive is the negative values. So ito, this is a positive value. So ito, this is positive 350 kasi tensile siya, and this is also positive 230 as well. Tapos meron ding opposite dito na sigma y that is going in the positive direction, you know. So in general, no, the way we set it up is, ay, mali yung ginawa ko. Dapat sa separate layer. Anyway, okay lang yan. So, ito, the way we do it is, just in case malito kayo, no? So, we have what we call as a positive plane and a positive, or a plane and a direction, no? So, if you look at this is actually a plane. We're just seeing it as an edge view, no? Parang edge view yung tingin natin sa kanya. So, this is the positive plane. So, ito yung negative plane. Tapos ito din, positive plane to. Ito is negative plane. So, if it's a positive plane and you're going in the positive direction, then positive times positive equals positive. So, kaya dito, we're going in a positive direction, positive plane siya. Kaya siya positive 350. Dito, we have a negative direction kasi negative 350 papunta sa left side. This is the negative plane. Kaya siya magiging negative times negative is positive 350. So, kaya positive din siya. Pero dito, hindi na, pwede na sigurong hindi nyo masyadong isipin muna yung positive planes and negative planes, no? Kasi 2D lang naman to. Just think about it na pagka positive yung pagka tensile siya, automatic positive, pagka compressive, negative. So, mas magagamit natin yung positive planes and positive directions pagka nagpunta tayo sa 3D stress state, no? Kasi gagawin natin yung parang 3D stress box niya. Okay? So ito dito we just established na ito positive 230. Tapos yung natin shear stress is kung mapapansin niyo nakasulat siya ganito, no, 480 tapos may dalawang directions na pa ganyan. Ibig lang sabihin nito is this shear stress right here is acting on the positive y plane moving to the left. Tapos ito dito nagbo-move siya on the opposite direction naman. So this causes it to move in a clockwise direction, tama? Pero dito sa explain natin, it's causing it to move in the opposite direction. And this makes sense, no? Kasi kung hindi siya nag-move opposite to each other, then magkakaroon ng rotation sa object natin. So hindi na siya naka-equilibrium. So equilibrium is dapat walang movement, walang net movement yung natin, stress element. Okay? So it's completely stable. Okay? So dito, it's 480 and we do positive siya. So on the y, dapat ito is positive 480. Tama? Tapos sa x naman, it's negative 480. Okay? So now that we've established the conventions, ang gagawin lang natin dito is we plot them, no, in this parang imaginary tau sigma plane. Okay? So again, itong plane na to, wala siya actually parang physical significance, no? This is more of an imaginary tool. So this is parang this was brought about because of the lack of parang wala pa namang computational na tools dati, and most scientists and engineers before us, no, the way they do things para mas mapabilis nila yung calculations is not actually through doing extensive math, no. Medyo graphical talaga ang approach nila kasi in fact kung magve-vector calculation sila, graphical yung approach, mas mas mabilis yung computations pag graphical approach. So kaya nagawa tong Moore circle, no, kasi it's a graphical tool to help us solve for the different values. Okay? So the first thing na ipa-plot natin is si sigma y muna. Okay? So sigma y is positive 230. So let's just say lagay ko lang dito, no. So this is 100, 200, 300, 400, 500. By 50s na lang para mas madali. Kasi, see, 1, 2, 3, 4, 5, 6, 7. Okay, so this is by 50s, no? So ito 400, 350, 300, 250, 200, 150, 150. Okay? So, ang first natin pa-plot, plot natin to, no? So it's positive 230 siya. And yung kasama niyang tau is positive 480. Okay? So that's 230 somewhere here. Tapos dito, it's so by 50s lang din natin gagawin ito, no? So let's do 50, 50, 100, 150, 200, 250, Di ba, by hundreds na lang. Mas madali. So, we do 100, 200, 300, 400, 500. So, somewhere dito. Tama? So, let's do that. And nasaan yung 230? 230 is somewhere dito, no? Okay? Parang ganyan. So, this is the first point natin, no? So, this point is 230 and 480. Okay? Now, we find the next point, which is 350. Tapos, we do 1, 2, 3, 4, 5. Somewhere dito siguro. Yan. And 350 siya. So, nandito siya. Okay? So, this is your 350 and negative 480 siya. So, negative 480 siya because it's moving in a clockwise direction. No? Tama? So, if you plot that, dapat na negative siya. So, ito yung coordinates niya. Again, this is a sigma tau coordinate system. No? Okay? So, now that we have that, ang gagawin natin is in close natin into a circle tong si itong coordinate plane natin, ay itong mga coordinates natin. Tama? So the way we do that is, kung i-connect mo to, kung saan siya nag-intersect dito, is actually siya actually yung center niya. Tama? Nag-agree ba kayo? So let me draw a circle no, para mas imagine nyo. So basically what we're trying to do here is nagka-create tayo ng parang ganyan. Okay? That's the circle we want to create. Okay? So, ito kasing si more circle, it indicates all the possible na orientation ng stress state natin. Okay? So, paano ko ba ma-explain to? So, think of it this way, no? Let's just say na, if ito yung coordinate system mo, and you have a vector na, kunwari, ito yung, let's say, one-dimensional lang tong stress state natin. So, if this is your stress state, kunwari ito, meron actually siyang two components, tama? Parang ganito. So, ang component 1 niya is itong, let's just say, the y component, and ito yung x component na. And let's just say na ito yung vector natin. Tama? Nag-make sense ba? So, ito yung vector natin. Pwede natin i-divide into y component and x component. So, for stresses, if the component is, if this is your surface, no? Kunwari ito yung surface, and this is the stress that is acting on the surface. If it's acting perpendicular to the surface, then we call it as a normal stress. Tama? So, yun yung sigma na tinatawag natin, sigma. If it's acting on the parallel to the surface, then we call it as sigma x, no? Or minsan, instead of sigma x, we call it as tau x. So, yun yung shear stress. So, a shear stress is a type of stress that acts parallel to a surface, while sigma y is a type of, or normal stress, are stresses that act perpendicular to a surface. Okay? Now, this is interesting because ang stresses naman natin, for example, if sa real world, pwede tayong mag-move ng coordinate system, no? Or in a way mag-rotate ng stress element natin. So it's the same stress pero iba lang yung kunwari ito, this is the same vector, no? Pero I can very well do something like kunwari ganito. Kunwari lang ito yung y prime axis ko. Tapos nandito yung x prime axis ko. Tama? If I do this, magkaiba yung niya. Kumbaga yung magiging component nitong So ito yung component niya dito. Ito yung component niya dito. So iba na yung parang shear ko and normal if I change the orientation of the orientation of the axis for which I am decomposing this vector. Tama? So that's akin to saying na yung stress element ko parang niro-rotate ko. This is my stress element, no? Ito, pag niro-rotate ko tong stress element, it's the same stress value or it's the same stress state, pero iba lang yung parang mga coordinate axis na ginamit ko. Okay? I hope that makes sense, no? So, actually, parang ang kunwari, for this particular case, parang mas convenient sa atin if, and this applies to almost all stress calculations, no? Mas convenient sa atin is if mare-represent natin sila lahat as a normal stress kasi ayaw natin mag-deal with shear stresses, no? So, if I do an axis that is something like this, kunwari, i-rotate ko yung axis ko, and this is my, kunwari, y prime prime axis, tapos nandito yung x axis ko, x prime prime. Then what I actually have is 0 yung tau ko. So my tau here, for this type of orientation, no, ang tau ko equals 0, and meron lang akong isang value, sigma y, which is equal to kung ano yung vector mismo. Tama? Which is very convenient sa akin kasi kumbaga hindi ko na-breakdown eh. Isa lang yung value ko, wala akong shear stresses, puro normal lang. This is what we actually call as sigma p. This is our principal stress. So ito yung hinahanap dito, no? Itong principal stresses 1 and 2. Parang hinahanap mo, iniikot mo tong stress box mo, naghahanap ka ng orientation, iniikot mo siya in such a way na mabubura lahat ng itong 480 na to. So definitely, di ba, kung same shear stress value to, pwede ko siyang ma-convert into something that looks like, and i-increase ko lang yung space ko, no? Pwede kong i-convert itong stress box na to itong stress element na to, pwede ko i-convert siya into something that looks like this. Hindi ko pa actually alam yung sagot, no? Pero pwede siyang ma-convert into ganyan lang. Wherein wala nang natirang stress box. Wala nang natirang shear stresses. Tama? Nagme-make sense ba yun? So think of it this way, no? So if I just move it slightly, i-rotate ko lang siya slightly, then ito, definitely magbabago yung value na yan. Ito, posible maganyan. Tapos pwedeng ito, lumiit yung parang value niya. So, pwedeng, kung naging 250 to. Tapos ito, hindi ko actually alam yung exact value parang dinidemonstrate ko lang. So, pwedeng maging 210 to. Tapos ito, naging 290 to. Tapos ito, naging 310. So, ito, parang inorient ko siya, nag-iba yung values, pero kung i-compute ko yung overall stress state na to, these are the same stress state. Iba lang yung orientation. So, ngayon, ang hinahanap ko is isang orientation na pag ginalaw ko siya, naging 0 na tong shear ko, puro ganito lang natira. Okay? So, ang natira lang sa akin is principal stresses or normal stresses lang. Okay? So, yung pag-ikot na yon, yung orientations na yon, yung parang pag-ikot natin ng axis, pag-ikot natin ng stress element, kaya natin i-represent dito sa Mohr circle. So lahat ng movement actually na yon is nandito sa circumference ng circle na to. So lahat ng possible combinations niya. Nagigets nyo ba? So ang difference lang sa Mohr circle is that for every 1 degree of theta, so kung iikot ko to ng 1 degree, itong stress element na to, 2 degrees siya umiikot dito. It's just because of the nature of itong graphical tool na to, no? So, the best way I can explain why that happens is if you look at it, kunwari, if you look at this, itong sigma y and sigma x, they are separated by 90 degrees. Tama? Pero kung titingnan mo dito, nung pinlot natin siya, they are separated by 180 degrees. So, every movement niya is actually equal to 2 degrees dito sa sa Mohr circle. Okay? So, ang mangyayari dito, since ganyan siya, so given that knowledge, no? So, sabi natin, hanapin natin itong principal stresses, no? So, again, sabi ko, principal stresses are defined as stresses that have no shear component, shear stress component. Tama? So, tingin nyo, if lahat ng parang combination of shear and normal stress values is located in this circle, ano yung part ng circle na to na magre-represent sa natin, principal stress? So, alin siya dito? Kaya ba natin ma-pinpoint?
Yung 100 plus sir, tapos yung isa dun.
Tama si Lloyd, no? Actually, hindi siya 100, baka mali yung scale ko, Lloyd, no? Pero gets ko yung point mo. Yung dito yung sinasabi mo, Lloyd, di ba?
Yes po.
Tsaka yung dito. Tama? So, that's correct, Lloyd, no? So, etong part na to, this is where you have zero shear stresses. Tama? Kasi dito, if you look at it, 230, nagbabago yung value ng itong X mo, tapos yung Y mo, pababa ng pababa while you are rotating it. Hanggang umabot siya sa point na zero na siya dito. Same dito, no? Ito, paakyat ng paakyat si 350. So, mali pala yung ano ko, no? Yung etong movement ko. Dapat pala bumababa tong 290. So, mga nagiging 190 siya. Pero hindi na nagmamatter yun, no? So, ito mga tumataas ng, kunwari, mga 400. Mga ganyan. Tapos, inaiikot mo siya at hinahanap mo yung orientation na eventually magzi-zero out to. Okay? So, parang ganun yung nangyayari, no? So, dito, kaya natin ma-solve siya, no? Kasi geometry na lang to eh. So, if you look at it, etong center na to, where is this located? So, you already have 230 and 350. So, if you take the average, makukuha mo yung etong center na to. Tama? So, 230 plus 350 divided by 2 gives you, kaya ba natin i-solve to? 230 plus 350. Paki-solve nga. Nagbe-brain fart ako. So, sige, kayo na mag-solve. So, ito actually yung center. Tama? So, ang coordinate nito is, let's just say, center 0. Tama? Yun yung coordinate niya. So, kaya din natin makompute tong parang radius na to, no? Kasi yung radius na to, if you look at it, ito yung radius, di ba? The radius by geometry, this is equal to, we can compute it dito, no? Pwedeng etong side na to or pwede rin dito na side. It doesn't matter. It should give you the same value. But dito, we can compute it as r squared is equal to, this is a squared. So that's 230. Etong, let's just say a squared to, tas ito b squared. Tama? So a squared na to, this is equal to yung center minus 230. Tama na, whatever itong c na na-compute. So that's center minus 230. That's your a squared plus yung dito, it's 480 minus 0. No? So that becomes 480 squared. Tama? So if you compute that, you should get an R value. Tama, no? So if you have R, kaya mo na ma-compute yung principal stresses. Kasi we have center. Center plus R gives you this value. Center minus R gives you this value. So kung compute natin yung sigma 1, and sigma 1, usually kung lower yung number, higher yung value niya. So ang sigma 1 is the largest, sigma 2 is the smallest. So if we have sigma 1, sigma 2, sigma 3, this is, kumbaga, ganito siya. Sigma 1 is greater than sigma 2 or equal plus sigma 3. Ganyan natin siya sinasabi yung principal stresses. No? Minsan, ganito yung pag-state din sa kanya. Sigma P1, sigma P2, sigma P3. Pero in this case, since ano tayo, 2D stress state tayo, sigma 1 is just equal to sigma max, while sigma 2 is equal to sigma min. Okay? So ito, sigma max will now just be equal to whatever itong center na to plus R. Tama? Kasi if you draw it, parang ganyan, this is R. Kasi circle yan eh. So sigma max is equal to center plus R. Sigma min is equal to center minus R naman. Tama? Kasi center minus R gives you this value. So baka mali lang yung scale ko, no? Hindi talaga 100 siya, pero yun. You can compute it using geometry. Tama? Tapos isa ding importante is yung tinatawag na tau max, no? So this is the maximum na stress, na shear stress na kayang ma-experience ng system na to. And it's important, yung shear stress is always important when we talk about plasticity, no? Because if you remember 176, parang naalala natin doon na the way metals actually deform is not through normal stresses, but it's actually because of shear stresses. Kasi 'di ba, if you remember, hindi ko alam kung maalala niyo pa 'to. Pero kung naalala niyo kung paano mag-deform ang isang material is actually because nagshi-shear yung mga tinatawag natin ano no, yung ano ba term dito? Yung shear planes natin. Ito. Slipping planes, I'm sorry. Ito yung mga slip planes natin. So the way kaya nagde-deform ang material natin is because of shear stresses that causes the movement of this slip planes right here. So ganun yung pagka kunwari may tensile test ka na ganyan. So I'm exaggerating pero parang ganyan no. Yung slip planes nagmo-move to produce the ano. So importante malaman din natin yung maximum shear stress. And in fact, mayroong tayong isang ano no ano bang tawag doon? Isang yield criteria na tinitingnan lang yung maximum shear stress. Okay? So later on ma-figure malalaman natin 'yon. So ito actually si maximum shear stress tinatanong din dito. So maximum shear stress tau max is just equal to the radius, no? Tama? If you look at it, ang maximum naman na kaya niya ma-achieve, whether it's positive or negative, is equal to this radius right here. Tapos opposite end dito din, equal din siya sa radius na to. So this is tau max. Ito rin tau max. Let's just say negative tau max. Sorry. So yun. Okay? So tau max is just equal to the radius. Tapos etong orientation of the principal stress, orientation niya is ilang degrees mo iikutin to. Okay? So if you look at this, para mapuntahan mo tong principal stress na to, kailangan mo ikot by this amount, no? Ito yung theta na yon. Pero remember na 2 degrees, every degree movement dito is actually 2 degrees movement dito. So kailangan nyo pa i-divide by 2. So ito, kaya ba natin i-solve through geometry? Itong angle na to? Kaya naman, no? So that angle is just equal to tan theta is equal to yung 480. Y tan is y over x, diba? So 480 divided by yung c minus 230. Tama? And let's just say tan 2 theta na para yung theta mako-compute natin is the actual theta in the stress element. Okay? So yan, ganyan i-compute natin. Pwede rin if you want, pwede rin cos theta, no? So paano nga ba pag cos theta ang ginawa nyo or kung cos theta, you'll now use yung A over R. Tama, no? Kung A to, B to, A over R siya. Tapos kung sin theta naman, it's B over R. Tama? So I hope you still remember your geometry, no? So you can solve it any way you want. Fiko, pinakamadali yung tan theta lang, no? Because it's just y over x. And alam nyo naman tong B na to, alam din nyo tong A na to. Okay? So we can compute for orientation. Kaya ma-compute. Ito naman yung stress state at 30 degrees clockwise. By the way, kailangan yung i-indicate, no? Kung whatever degrees na na-solve nyo, sabihin nyo kung anong direction. So for example, ito, we are moving in the counterclockwise direction. So n degrees counterclockwise direction. Tama? Kahit dito, ganun din naman. So pwede din kayo mag-solve actually dito, no? So compute nyo itong theta na to. It will give you the same theta dapat or 2 theta. So that becomes n degrees counterclockwise direction. So ito naman, what is the stress state 30 degrees clockwise from the plane? Okay, so if this is our, ito yung stress state natin as represented by this 2D element, then we just need to move n amount of degrees clockwise. So sabi kasi 30 degrees daw i-move natin. And we remember that for the Mohr circle, it's always 1:2 yung movement niya. So kung 30 degrees i-move dito sa stress element na to, we are moving 30 degrees clockwise. Then we should move 60 degrees clockwise naman. Okay? And kaya nyo na siyang i-solve, no? Kaya ba? Kasi kung geometry lang din ang movement nito, no? So we just move 60 degrees away. And we should find Ito yung hinahanap natin. Para hindi tayo magulo. Pwede sigurong ibang kulay. So gusto natin mag-move 60 degrees. Tapos hinahanap natin anong value dito, anong coordinate dito. So blank and blank. Tapos sa kabila, kung ano din value dito. It's blank and blank. So yun yung magiging stress state niya if we were to move it 30 degrees sa stress element na to, which is translate to 60 degrees dito sa sa Mohr circle na to. Okay? Tapos last, I think this is the last, no? Plot and label. Ay, okay na pala. So yun, hindi ko na-expect na, akala ko kasi pre-rec ang 102. So inisip ko pwedeng i-review ko na lang yung Mohr circle, no? Pero apparently, ngayon pa lang kayo nagtitake. So, naubusan tayo ng oras, no? So, i-check ko lang yung schedule natin. Kasi baka, may two options tayo. Pwede tayo mag-meet on Wednesday next week, pati Friday. Or, meron kasi akong recording from the previous previous year, explaining stress states din. So, pwede ding ipakita ko na lang yung video na yon. Tapos on Friday, since napanood nyo ng video, pwedeng mas mabilis na yung discussion natin. So, discuss tayo konting stress state plus, let's check the schedule. No? Wait lang. Browser. Nakikita nyo ba yung Uvlet page natin? By the way, if you have classes, baka kailangan nyo nang umalis, okay lang. You can go now. Pero if you have time, pwedeng mag-stay muna kayo. Nakikita nyo ba?
Sir, black lang po yung screen.
Black lang. Bakit kaya? Ayan. Okay na?
Okay na po.
Okay, thank you, Lloyd. Si Lloyd yun, no?
Si Nico po yun, sir.
Hindi ko pala, sorry. Hindi ko pa kabisado
Nagalit
yung...
na si Lloyd sir.
Sorry. Hindi ko kabisado yung boses nyo pa sa Zoom. Pero, eto, check natin yung course guide, no? Kasi ngayon, where are we now? Dapat, October 1 ngayon, dapat stress state na tayo, tama? Pero, October 6, ano bang calendar? Next natin meeting is October 8. So, October 8, pasok na tayo. I think kaya naman pala. Okay lang pala. Kasi pwedeng sabay yung discussion natin ng Tresca criteria tsaka yung 3D stress state. Kasi kulang na lang natin sa stress state is yung practice worksheets ng 3D stress state. Okay, so pwede. Meet tayo 3D stress state. Tapos on October 8, discuss natin konti 3D stress state. Tapos yung application ng yung stress state na yun onto the Tresca and von Mises criteria. Kasi related tong dalawang to. Okay, so okay lang. Hindi natin kailangan mag-ano. Pero gusto nyo ba na i-send ko na rin yung recordings from the previous year? Would you think it would help? Tingin nyo.
Pwede lang, sir.
Go
Pwede
lang?
naman.
Sige. Send ko na lang
Yes
din.
po.
Okay, so yun lang. Thank you for coming in today, class. Medyo madami tayo, no? So, I hope this was productive. Tapos, if ever nahirapan pa rin kayo kasi hindi to full-blown discussion talaga, no? Kasi I was expecting na sa ES 102 to i-discuss. Pero kung nahirapan pa kayo, then don't hesitate to message me. Tapos, I'll try my best to answer all your questions, no? Okay? So, thank you again for coming today and I'll see you on October 8. Tapos gamitin na natin tong Zoom meeting na to, itong recurring meeting na nilink ko. Okay? Pero before we end, okay lang ba kayo sa format natin ngayon? Hindi ko talaga binibigay yung final answers, more of parang guidance lang and direction.
Yes, sir.
Okay na.
Okay.
Sakto lang naman, sir.
Okay, thank you sa feedback nyo. Okay, so with that, let's end our session and see you next week. Thank you.
Thank you po.
Thank you, sir.
Sir.
Thank you, sir.
Thank you, sir.
Okay, ingat.
Sir, may question pala ako.
Sige, go
Konti
ahead,
lang.
Lloyd. Go ahead,
Sir,
Lloyd.
yung number 3 po, pwede pa ulit po nung exam, nung parang sample mo, sir.
Anong number
Ay,
3?
yung
Dito
number,
sa
part 1 po. Problem 1 dun sa module 2.
module 2?
Yes po.
Sige, hanapin natin, Lloyd. No?
Yung UTM